right, so today we are going to look at the example problems for chapter 20. Hopefully some of you, well, it's the only one of you in here, has looked at it online. But that's the idea for every Friday, right? I'm going to post a packet of problems for examples that will be posted Wednesday after class ends. And on Friday, I'll go through them, or at least most of them. I might not always go through all of them. Normally, I only spend about 25 minutes doing these because in class, you would have spent 25 minutes doing them yourselves. That isn't happening because global pandemic. So this chapter is all really about these two equations I have in the upper left of the screen and the one beneath it, that's how they're related. The first between two charged particles, which is Coulomb's law, and the electric field from a particle, which doesn't have a fancy name. So yeah, I'll just jump right in. This first problem says we got three charges. They don't label the middle one, but I'm labeling as Q3 just to keep my own sanity. And they say in this figure, Q2 has no net force. What is Q1? So if there's no net force, what that means is the sum of forces is 0. So we're dealing with forces. I'm going back to physics 1. I'm going to start this free body style. I'm going to talk about what forces are acting on it. See, if we're looking at those no net forces on 2 is going to be acted on by two different forces. The Coulomb force between 1 and 2, and the Coulomb force between 2 and 3. Now, keep in mind this whole how we got to keep track of the direction, right? So the force between 1 and 2, both 1 is positive and 2 is positive. And so these two are going to try to repel each other. What this means is the force between 1 and 2 is going to be to the right for this guy because it's going to be pushing away from 1. It's not like it's in the positive direction because they're positive. It is away from 1 because they're both positive. When dealing with these forces, I don't normally, the version of these equations I put up don't have the absolute value signs around them, but I normally only plug in absolute value signs there and just work out direction from looking at the picture. Once again, drawing is always your friend. Now, there's also going to be a force between charge 2 and 3. But the force between 2 and 3, we have one positive, one negative. So this would be an attractive force. So the force between 2 and 3 will be that way. It should be a straight line and not up at an angle, but I can't draw a straight line apparently. But it'll be attractive because they're opposite. Now just going back to the whole idea, the sum of forces, we have for horizontal, right minus left, for vertical, up minus down. I can say that if I look at this, I have whatever forces to the right minus whatever forces to the left. That's going to be what the sum of my forces is, which in this case, there's no net force, is 0. So that means it's going to be F12 minus F23 equals 0. This means they obviously balance, that F12 equals F23. Now, I could go and try to just start solving for each force individually. No, I don't know the charge of Q1 and I don't know the charge of Q2. So if I start trying to find each force individually, knowing that each force, that F12 is KE Q1 Q2 over R squared, and F23 is KE Q2 Q3 over R squared. Well, these R's are different. I'm just going to put them as R12 and R23 to keep track of them. I don't know Q2 in both those equations. So instead of trying to plug in numbers and solve for the force, I'm just going to put the whole thing in here. Now, before I do, no, I didn't do it that way. Okay, so I'll do that. I'll say KE Q1 Q2 over R12 squared equals KE Q2 Q3 over R23 squared. Now, both sides have these. I'm going to divide both sides by KE, canceling that out. And I'll also divide both sides by Q2, canceling those out. And that's going to leave me with Q1 over R12 squared equals Q3 over R23 squared. Now I should be careful. I kind of did something I was messy with here. And that's the fact that Q3 is negative. And I should have done it from the get-go. That negative sign kind of represents direction, but not really. I recommend always absolute valuing. So when I go and plug in, I'm going to say the absolute value of Q3 because it's a negative. I'm just going to keep the positive term. Now my goal was to solve for Q1. Right? Yeah, my goal is to solve for Q1. So I'll take this and I'll multiply both sides by all 1, 2 squared. And then plug in. That Q1 equals the absolute value of Q3. Let's see, Q3 is -2 nanocoulombs. So I'm just going to make absolute value. I'm going to drop the negative sign. All 1, 2. All 1, 2 is in between 1 and 2. Now, if you note, they don't give that distance. They say from 1 to the middle is 10 centimeters, and from the middle over is 10 centimeters. So that's going to be 20 centimeters, or 0.2 meters. And all 2, 3, 0.1 meter. I can do that math. That's going to be 2 nanocoulombs. And I know I should probably be converting my nanocoulombs to coulombs. I didn't, just because I can just put my final answer in nanocoulombs. It'll be fine. 0.2 squared is 0.04. 0.1 squared is 0.01. And the answer is 8 nanocoulombs, or 8 times 10 to the -9 coulombs. Really, these problems, what makes these problems complicated isn't the Coulomb's law bit. The Coulomb's law is kind of plug and chug. It's just dealing with vectors and forces again. All that stuff that made chapter 4 complicated in physics 1, that's what's going to make chapter 20 complicated in chapter 20. Yeah. Any questions on that? You good? All right.
Good.
Since you're getting a one-on-one class, and all the people who watch the video can feel bad when I mock that no one else showed up. Let's go to the next one. Now that one was kind of simplified in the fact that it was one-dimensional. A lot of the time when I give these problems, and so this is only my since it's only my second time teaching this class, there's less old exam problems showing up anywhere because I've only written one set of exams for everything, and I didn't work the old exam problems into these packets yet because I figure when I go over last semester's exam, you'd see them then. That being said, the exam problems were very similar to this. I will upload them soon. But this next one was more complicated because it actually deals with a two-dimensional system where I have Q1, is that 2 or 3? That's 3, Q3, Q2, oop, that was my thing, not my Q, Q4, and the middle one's positive, QC. And I say, okay, I got this square, each side is 1 centimeter. I gave the magnitude of each charge, -2, -2, +2, +2 nanocoulombs. And I say, what's the magnitude and direction of the force on the middle? So I'm going to do the generally same basic idea. But there's a trick to this problem that's going to simplify it, but I'll come back to that. And I'm going to say, okay, this center one is going to get attacked by 4 forces. And instead of calling them like here I did 2, 3, 1, 2, I'm just going to call force 1, 2, 3, 4. I'm not going to bother with 1C, 2C, 3C, 4C. Just because I'm going to be writing enough stuff here, I want to minimize mess. And I'll say, okay, let's figure out each force. Each force is going to still go by this KE, Q whatever QC over R squared. I'm just going to say QN. I'm just going to put it to the N, where it's going to be whichever one, 1, 2, 3, 4, respectively. Now, before I do anything, I like to work out direction. Now, between 1 and C, and I'm color coding it to match the picture, although I guess the picture is green, not blue, but my green doesn't show up that well, so you're getting blue instead. And I'll say, okay, between 1 and C, we have a negative and a positive. That's attractive. Between 2 and C, we have a positive and positive. That will repulse. Between 3 and C, we have a positive and a negative. That's going to attract. 3. And between C and 4, we have a positive and positive. They're going to repulse. And what my picture shows is that these kind of point together. That F1 and F4 are parallel. And F2 and F3, they're also parallel. They point right in the same direction. Also, if we look at our values, we're going to, once again, I use absolute value. But the magnitude of these forces is negative 2 nanocoulombs, 2 nanocoulombs, negative 2 nanocoulombs, 2 nanocoulombs. So with this absolute value, that means for all of them, for F1 or F2 or F3 or F4, the magnitude of them is still KE 2 nanocoulombs times, what's the center one? 1 nanocoulomb over R squared. They're all going to be identical. The distance will also be the same for all of them because it's in the middle of the triangle. Now, I do need to know that distance, and I'm going to go to a second picture for that, where I'm just going to draw half of it. Because I know this right here is 0.01 meters. And I know this here is 0.01 meters. And so I can find this whole length using Pythagorean theorem. Which I did in a weird way. Huh. I did it in a different way on there, but I'll just do it this way. And so I'll say this whole thing, which I don't want to call O because I want to confuse it with this. I'm going to call this whole thing the hypotenuse. The hypotenuse squared is 0.01 meters squared plus 0.01 meters squared. And I'm going to kind of skip over the math, but I'll square this, add together square root, and that'll be 0.01 times the square root of 2. I'm basically, I just know that because of trig identities. If people want me to walk through that slower, I can. But if you do that math, that's what it is. Oh, sorry, that's what h is, not the square root of h. The thing is, O is just this distance here. So O is half that. So my O value is 0.01 meters square root of 2 over 2, which is going to end up being 0.00707 meters. Now that I know that, I can solve for all these f's. Because going back, actually, I'll do it down here. Well, I'll go back up here. That all of these f's, I said was KE, 8.99 times 10 to the 9th Newton meter squared per coulomb squared, times 2 nanocoulombs, 2 times 10 to the negative 9 coulombs, times 1 nanocoulomb, 1 times 10 to the negative 9 coulomb, over R squared, over 0.00707 meters squared. Now, apparently when I did this, I didn't actually solve for that number. I went straight to the next step, and I plugged in after the fact. So I'm just going to do it now. 1e negative 9 times 2e negative 9 divided by 0.00707 00707. But the thing is, that's just the magnitude of each one of these. But I still got to add them together. These are full vectors, right? So I'm going to go and look at them and say, okay, let's look at these full vectors. And I'm just going to draw just my center guy. My F1 and my F full, I'm just going to say, since the magnitudes are the same, I'm just going to say this is 2F. And my F2 and F3, because they're all the same, I'm just going to say that's also 2F, just to make life easier. But when I look at this, they're up at some angles. I'm going to have to split them to components. So I'm going to say this top guy is going to be a 2Fy and a 2Fx. This bottom one is going to have a 2Fy and a 2Fx. Because if anything's not straight along X or straight along Y, I want to make sure I break it into components.
Wouldn't it be at 45 degrees?
It is at 45 degrees. Yes, it is. But before I even say the 45 degrees, let's just look at these Y values. That up and down have the same magnitude, just opposite direction. That this 2Fy up and this 2Fy down are going to cancel each other out. And so the net force on this thing is just going to be full Fx. And so I'll say that means it's going to be full times whatever that force was, and it's the x component, the cosine of theta, which, as you just pointed out, is 45 degrees. Which I see why I didn't plug in some of the numbers ahead of time, because some things canceled out. And you get the magnitude to be 0.00102 newtons, which I didn't write it out, but I'm just looking at this in the negative x direction. Oop, that corner is not in focus. There we go. I mean, I kind of did some algebra tricks to make it easier. I didn't just be like, oh, let's plug in each one. But they all canceled out. And that's something to keep in mind when doing these problems. If vectors cancel out, use that fact. It can simplify your math. Any questions from either one of you? We now have a second person.
I think I got it.
Right.
It's just more complicated free body diagrams from chapter 5.
Yep. To be fair, that's going to be a thing this chapter, and then they're going to disappear again. Not everything will be vectors. They'll come back again later too, but it's only sometimes we're going to have to deal with vectors. Okay. Now these were just dealing with Coulomb's law. This was just the idea of, oh, I have to bring my recycling bin back up. Yeah. So this was just the idea of forces. But the next one, and I'm going to probably do 3 and 4. I'm probably going to go more than 25 minutes, despite what I said. Are going to be dealing with instead electric fields. See, the difference is when dealing with electric fields is you don't necessarily have a charge at the point you're looking. And to be fair, I could have done electric fields for the first one too. It would have worked. This problem number 3 says, what are the strength? That's bad English. What is the strength and direction of the electric field at the position indicated by the dot in the figure? So, we have two things. Are they labeled? No, they're the same. They're both the same charge, so I'm just going to label them as Q. And they tell us we're halfway between 5 centimeters and we're 5 centimeters out. Now that's again going to be, the distance is going to be this here. So I'm going to do it the same way. R squared equals 0.05 meters squared plus 0.05 meters squared, which is 2 times 0.05 meters squared. So when I square root it, R is 0.05 meters times the square root of 2. Which is, I mean, if I pull that last one up, last time it was 1 times the square root of 2 divided by 2. This time it's 0.05 times square root of 2 divided by 2. So it's, you know, the same value. Now, if I'm looking for electric field is KEQ over R. Well, I'm still going to absolute value, R squared. So let's look at the direction again. Electric fields always point away from charged particle, from positive particles. And so the lower one is going to be up this way. The upper one is going to be down that way. And I'll once again break these into components. I'll say, I'm just going to call this E lower and E upper. That the lower one has an E lower Y and an E lower X. The upper one, and yes, I have my upper now as my lower, and my lower is now my upper, but I'm saying this is the lower one, so it's pushing this way. This is my upper one, it's pushing that way. Would be E upper Y, E upper X. And you see something very similar from the last problem. That if I work out the vectors and say the total electric field, if I say the total electric field is the E upper plus the E lower, well, I would say in X, it's going to be this plus this. In Y, it'll be the up minus down. And just like the last problem, my total electric field in Y is going to cancel out. Because the charge Q, both Q's were the same value. And since both Q's are the same value, they're just going to oppose each other and cancel each other out. In X, there's going to be 2 of them. Well, I'll just write it out. There'll be ELX plus E upper X, which is EL cosine theta plus E upper cosine theta. But since they both have the same charge, these both E's are the same. This is really just E cosine theta plus E cosine theta, or 2E cosine theta. And so it would be 2 times Coulomb's constant, Newton's Coulomb squared meter squared, times the charge 1 nanocoulomb over R squared. Oh, cosine 45. Did I go off the edge? Ooh, I'm a little low. Once again, drawing your pictures make these easier. If I didn't draw the picture, I probably would have gone, solved each one. Once I solved each one, found the Y component of each one. But why bother finding the Y component of each one? I can just look at this picture and say, these cancel, these 2 add up. Draw your pictures. It'll make your life easier. Questions on that? Okay.
Nope, I got it.
Let's look at number 4. Traditionally, I normally don't do all 5 problems in the packet. I sometimes do, sometimes don't. Normally the fifth one is a bit more of a trick to it, and it's a little more complicated. I'll probably only do the full today. I forgot the last one's kind of interesting, but I'll probably still only do the full. In class, I would have actually been like running out of time already because it's already 3:25, and I might not even gotten to the fourth one. I probably would have skipped this one, but I'm gonna do this anyways and say, okay, what we got here is we got a wall, we got a string. You know what? Let's actually, and a positively charged particle. A small sphere of charge 68 nanocoulombs. And mass of 5.8 grams. And I'm just converting these to kilograms and coulombs as I go. It's attached to a light string and placed in a uniform electric field E that makes an angle of 37 degrees with the horizontal. So my E is that way. The opposite end of the string is attached to a wall, and the sphere is in static equilibrium when the string is horizontal and is in the figure. Step A, construct a free body diagram for the sphere. It's kind of weird that I left that in because normally I have people work it out, but we can do it. If that's what we have, well, I can look at what's going on with forces. The most obvious one is that there's a string here. So there's a tension holding it back. That should be right along the string, but once again, I can't draw straight lines apparently. They also give a mass, which means gravity is going to affect it. But this is a charged particle in an electric field. Anytime a charged particle is in an electric field, it feels a force equal to EQ. So this red arrow is also really can be a force arrow, where the force equals EQ. Now, I'm going to break this down a little bit more and say, okay, tension is along X, good. mg is along Y, good. This EQ force is up and at an angle. So I'm going to say, you know what? This free body diagram needs to be split up. It needs to be turned into the things right along X and Y, albeit negative. They're fine, but this EQ needs to turn into an X component, which I'm just going to call this one F of X, and a Y component. Now it says it's in equilibrium and wants the magnitude of the electric field and the tension of the string. Well, that's easy enough to do. Equilibrium means that the sum of forces is 0, which really means that the sum of forces in X is 0 and the sum of forces in Y is 0. And once again, this is chapter 4 of Physics 1, which, David, I don't think you had me for Physics 1 if I'm not mistaken. At least I don't remember your name off the top of my head.
Yeah, I didn't. I took Physics 1 at another college.
Okay. If there's things from Physics 1 that's different and seems weird, let me know, but I assume you did this the same way there too. It's the standard. And that's, I can look at my free body diagram and say X is everything to the right minus everything to the left. Y is everything up minus everything down. So in X, I'll say it's my F of X minus T equals 0. And in Y, it's my F of Y minus mg equals 0. Well, this F of X and F of Y respectively is going to be, well, F was EQ, so it would be EQ cosine theta and EQ sine theta. So EQ cosine theta minus T equals 0 and EQ sine theta minus mg equals 0. Now, I was asked to solve for E and T respectively. Well, this guy has both E and T in it, so I would ignore him. And this guy has only E in it. And for those of you who did have me, being right now Tim, but whoever's watching online, this may look very similar to the Doctor Strange problem, I think is the one that was on the homework. That was the same, except missing this force. And I had a few others like that also. I can't remember which ones I had on the homework off the top of my head. But it's the same basic idea that I'm going to rearrange this. I'll add mg to both sides. Oops. And then I'll divide both sides by q sine theta. Am I still on the page? I am. And from that, I can just plug in 0.0058 kilograms times 9.81 meters per second squared over 68 times 10 to negative 6 coulombs times the sine of 37. And like really all this is forces from physics 1. It's just, ooh, here's another new force. Look, we got tension, nothing changed. Gravity, nothing changed. This is really more of the same. Meanwhile, part B is part C is what's the tension. I'll just add tension to both sides of this equation and say EQ cosine theta equals T, which means 1390 times 68 times 10 to negative 6 coulombs times the cosine of 37 equals T. 0.0. And I'll get that answer. For those of you who haven't had me before, which once again, I assume other people are watching this video, but it's one person live, just so you know, on Vanco Hall right now, you will find this, a typed version of the solution that is a little neater than my handwritten scratch. That is getting posted. Although I guess if you're watching the video later, this link is attached to that document. So whatever. It is online. That's the secret to these problems. They're just force problems. I don't know. I almost never give one that isn't equilibrium. I can't think of one off the top of my head that is accelerating, well, at least for this chapter. I'll touch on when they are accelerating next chapter when we start getting into potential differences. But that's next chapter, potential differences? Yeah, next chapter is potential differences. But that's the general idea. Make a free body diagram, do your whole right minus left, up minus down thing. But it's just, here's the force. For giving the force, you're either going to use, you want to do a force, you're going to use either one of these. Let me get my pen. Nope, that's not the right thing. Pen. No, it's just this. Yep. If you deal with forces, you get one of these guys. Oh, that's not see-through. If you're dealing with electric field, you can deal with that guy. Those are the equations. And really, those are the only equations you're going to have to deal with. Other than the fact that they probably should have been absolute value. But I kind of put those on seconds before I went on. Threw that onto a document and didn't think about it. Okay.
All right.
As I said, I'm not going to bother with the fifth one. If you want to work on it, you can. The solutions are here. It's kind of an interesting one because it has dealing with forces from both of them. It gets a little complicated. But I usually make the last problem more complicated and always be harder than anything I've given an exam. / sometimes it's problems I gave on an exam and were too hard and it was a mistake and I shouldn't have. But that won't happen here because there's only been one set of exams before. Once again, second time ever teaching this class here. But yeah, I'll stop there. Hopefully that'll help for when you go to do homework. Your homework is due Wednesday. The lab has now been posted, so you can see the first lab. It's a little different than most labs, mostly because you are literally drawing pictures for the lab, just the way it is. But that is up, so you can get working on that. But otherwise, that's that. Next week, we get into potential differences in capacitors.
Perfect. All right.
All right. So